Hi, in this video I'll be talking about Java HashMap for its internal structure and characteristics. In this video, I'm assuming that you know what an array is, the direct memory access. I'll review it still, we'll go through it very briefly. You're comfortable with binary arithmetic, just the very basics. For instance, you know how many bits it takes to represent a certain numerical value. And you know HashMap. You know how to use it. You did use it. There are many good, excellent resources for this. If you'd like to review many blogs, articles, videos, so many resources, and I can always answer your questions here. The purpose of this video is to provide a technical insight on HashMap for its more effective use, for its better use. So what exactly is going on behind the scenes when you're doing an operation on HashMap? For instance, what exactly is happening when you're putting an entry to the HashMap? What's going on when you're getting one? How things are searched? How are these entries organized? What is the cost of these operations? The time efficiency? How come HashMap is providing constant time access for your operations, single entry operations? Why the contract between hashcode and equals so crucial? What goes wrong? Where, why, how, if you break that contract? How a poorly overridden hashcode can degrade the performance of your HashMap. You can be obeying the contract between the hashcode and equals, but you still can have a poorly written hashcode. We'll see all of these in this tutorial. A HashMap is, before being anything else, it's an array. An array is a sequence of indexes placed one after the other, physically one after the other in the working memory in RAM. Each of these cells have the same size, one specific constant size. So in order to reach any one of these indexes, all you have to do is to know to have the beginning of this table, the address it starts, the sequence, and then calculate the offset. For instance, in order to reach the fifth element in this array, you multiply the cell size by 5 and then add up to the beginning address, and that's it. This is constant time access. This is direct memory access. It's constant. It gets you to that cell at constant time, whichever the cell you're going to. This is a very powerful structure. This is a very basic structure. Every programming language has array or a structure like this. It is very, very powerful. It is at the bottom of many data structures, including HashMap. A hash as a data structure uses this feature, uses an array, puts it in a different use, extends its use so that you can reach these cells not just by these indexes, but the keys of your own. This is what a hash is. Each of these cells is called a bucket. So a hash is a table of buckets. The entries in the HashMap, the key values, or in other words, the entries, or in other words, these nodes, they each go into one of these buckets. At a certain point of time in execution, a bucket can be null, nothing in them, there's no entries in it, or it can have one single entry in it, as in this case, for example, or it can have two or more nodes in it. Ideally, this shouldn't be the case. Like there should be at most one entry in each bucket. These nodes should be well dispersed throughout the buckets. It's because we don't want to spend time searching through the nodes to find the one we are looking for. Once we go to the bucket, once we find the right bucket, we should be done. However, we can't always avoid this. We can't always avoid collisions. This is called a collision. When an entry goes into a bucket that is already occupied, that's a collision. Collisions are not desirable. We can't guarantee to avoid them. However, we can reduce the possibility of collisions. When there are multiple nodes in a bucket, we have to have some means to organize them. That structure is a linked list. Nodes linked one after the other in a linear fashion. It is a linked list of HashMap's own, something internal, one that HashMap implements and uses internally. This node class is a nested static class of HashMap within HashMap. So it's all internal. It isn't the linked list that we know in the collections hierarchy. So now the access time, computational complexity of a linked list is linear in the number of nodes. This isn't good enough for us for HashMap when the list gets longer and longer, if it does. And if that happens, the magic number here is 8, then these nodes are organized as a binary search tree. The linked list is torn down right there and then, and they are organized as a binary search tree, a red-black tree to be exact. The access time of a binary search tree is logarithmic. It is faster than the linear search. Actually, it is the fastest possible, theoretically. So, if, however, afterwards the number of nodes, the size of the tree goes down to 6 or less, then Java HashMap decides that it no longer is meaningful or feasible to maintain the tree structure, and it goes back to a linked list. Each of these nodes holds one entry and one entry only, one key value pair for each node. So in the data portion is the key and the value and this hash. We'll talk about this hash a little later, but for now we can safely think of it as the hash code of this key object. This is the same for both the 3 nodes and the linked list. The nodes on the linked list. There's no difference as far as the data portion goes. Their links are different because of the different structure they maintain, but that's not what we're interested in. The data portion of on any node on a hash is exactly the same. The size of the hash is always a power of 2. This is for the bitwise operations. It's easier when it's a power of 2. It is the default size of a hash map is 16. From the moment it's constructed and any time after, it's a power of 2. When it's resized, the size is increased to another power of 2.